In this one page of notes about the magnitude of the equilibrium constant, I'll be covering two main things. The first are the numerical values of K and what they mean. The second is a practice problem where the K value is much less than 1 and how we can use some mathematical simplification to solve for the equilibrium partial pressures or the equilibrium concentrations. This is part of Unit 7 on equilibrium, Topic 5 in AP Chemistry, but it also could be part of your college-level chemistry course on equilibrium. So first is when the K value is less than 1, the equilibrium constant, it means that reactants are favored at equilibrium. And I've covered that in a previous video with some graphs. And what that means is that your reactant concentration or partial pressures are greater than your product once equilibrium has been established. And then the opposite would be true. Products are favored if the K value is greater than 1. And that just means that my product concentration or partial pressures are greater than my reactant once equilibrium has been established. You could also have a K value that's close to 1, and then you could argue that neither reactant or products are favored. And all that means is that your reactant concentration or partial pressures are about the same as your product. All right, the next is going to be when the K value is very small or very, very large. And what that means is the first one is that the reaction, I'm just going to put RxN, barely proceeds. And then the opposite of that would be that the reaction essentially goes to completion. And that's sort of what we've been probably thinking before we even knew what equilibrium was. We treated all reactants turning into products as if they went to completion. So what does that mean in terms of your concentrations? It just means that this one, my product concentration, is very low. And then this one just means that my reactant concentration is very low once equilibrium has been established. Now, the values that the K needs to be, I go back and forth, but I would actually argue that to the -4th, sometimes maybe the -3rd is fairly small, but -4th I feel more confident, or 5th. And then the opposite would be if this has a positive 4 or 5 as a value. All right, so let's move on to then this equilibrium problem down here. So if you want to pause the video and write it down, and how we're going to solve this using some simplification to get to our final answers. All right, so first thing let's do is let's write the equilibrium expression for this reaction. And since we're going to have pressures, or partial pressures, we're going to call it Kp. So you're going to have pressure of my bromine monochloride and then squared. And I went over how to do this in a separate video if you want to go back and watch any of those. And then the pressure of my bromine and the chlorine, and then the diatomic chlorine. And those are partial pressures. And then the Kp, we were told, is 1.11 times 10 to the -4th. So it kind of fits that criteria. Next is going to be putting in our initial concentrations, or in this case, our initial partial pressures. So this one is 755 torr, and then this one is 735 torr. Now, for a Kp, we want to have ATMs, and then the temperature doesn't really affect it except for the fact that it goes along with the K value. The temperature is more of a disclaimer because this K value would change if the temperature changes, so you don't really use it. And then the other thing is that there was 0 torr, or no, at the start, no products to start with. I'm going to show you how to convert from 755 torr to ATM, but then I'll just tell you the answer for the other one. So this is actually in another video I have on how to convert gas pressure units. In case you don't remember, you can watch that. And I have 760 torr for every 1 ATM. And then this is going to end up giving us 0.9934 ATM. And that's going to be the partial pressure of my bromine to start with here. So 0.9934. And then I'm just going to tell you the other one converted, make it a little faster for the video, 0.9671 ATM. All right, we could calculate a Q, and I'm going to do that just to tie in another video that I had on this Unit 7, or equilibrium topic. The numerator would be 0 squared, and then the denominator would be 0.9934, and 0.9671. In the end, though, this equals 0, and so then the Q is less than the K. Even if the K value is small, 0 is still lower. And what that means is now we're going to say that it shifts right. We're going to produce some product. So we're going to do that with the stoichiometric ratio, minus x, and plus 2x. And I've done a Rice table in a previous video. I'm also going to add in the EX versus the E, meaning the X with the value. And what I mean by that is 0.9934 minus X, and then 0.9671 minus X, and then just 2X. So that gives me another space here to put my final answers down here when I have them. So we're going to come back and fill those in a second here. We have to start to actually solve the mathematical portion of this now. So the KP, I already have this expression over here. I'm just going to put the numbers in for that. Let's kind of top this off a little bit higher here. So let's box this out for you. This is where I'm putting the values into there. And so the top is going to be 2x. And it's going to be a small value for x, but it's going to be something. And then 0.9934 minus x in the denominator there. And then 0.9671 minus x in the denominator. And then all of this is going to equal 1.11 times 10 to the minus 4th. All right, now because the K value is small, this is something called an approximation, and we'll check the error of this later. We're going to basically ignore that x. And why we can do that is because we're going to assume that this concentration and this concentration is not changing much, and it'll simplify the math, and we can just solve for the 2x in the numerator there, which will turn into 4x. So you're going to end up having 4x squared in the numerator, 0.9934, and 0.9671, and then that's going to equal 1.11 times 10 to the minus 4th. Now, I'm going to just kind of move on to like the next steps. I'm going to kind of go like dot, dot, dot. This is going to equal then 4x squared is going to equal 1.066 times 10 to the minus 4th. And then you would divide both sides by 4. And then you would end up square rooting both sides like that. And I'm just going to quickly go down to then the final answer for x is 0.00516. So if I put these back into here, I'm going to do this one first because that's kind of the easiest one. So I'm going to take that times 2. So my pressure of my bromine monochloride is just going to be 2 times 0.00516. And then that will be a value of 0.01032 ATM. And then to get the other ones, I have to subtract the x. I'm just going to show you one of them. So the partial pressure of the diatomic bromine is going to be 0.9934 minus 0.00516. And that final answer here is 0.9882 ATM. And these are our final answers. These are the partial pressures at equilibrium. And you can see that it didn't go down very much. And then next is going to be then, I'm just going to tell you the other answer is 0.9619 ATM. And that's our final answer for that one. And then the last thing I'm going to do is just check that this was sort of like appropriate or okay. So I'm just going to erase this little section right here. And I'm going to do what's called the 5% rule, or double check that this approximation or this summation that we just did worked out okay. So we're going to do percent kind of error. And what we're going to do is take our x value. So you take your x value and then you divide it by one of the initials. So in our case, it's not an initial concentration. It's actually an initial pressure. But you could also have an initial concentration. And so our x value, I'm just going to substitute this in, is 0.00516. And then I'm going to take the smaller of the two initial pressures because we had two different initial pressures here, 0.9671. ATM. Because if this one's fine, then the other one's fine. And what we're going to get then is we get basically 0.5%. And as long as this is under 5%, we are good to do this approximation back here and just get rid of the x. All right, so in this video, again, we went over the magnitude of K and also a unique way to solve for it with this equilibrium pressure problem where we have a K value that's very small. And we also have, again, a summary of what those different values are. Well, if this video helped you to get 1 page of notes for the section 7.5, watch the other videos that I have, and feel free to subscribe, like, or comment. And good luck in your chemistry class, and off to 7.6.